Welcome back. In this video, we're going to talk about how we can use infrared spectroscopy to confirm the presence of functional groups within our organic unknowns. As we begin to think about spectroscopy, it's helpful to remind ourselves what we mean when we say electromagnetic radiation. So radiation is a general term for light. And often if you think of light, you'll immediately think of visible light because we can see it with our eyes. But if we consider the entire electromagnetic spectrum, we actually find that there are many different types of light, which have different unique energies. This includes IR, X-rays, gamma rays, microwave radiation. So as a quick Gen Chem refresher, remember that the energy of light is directly proportional to its frequency. So high frequency light has higher energies, and lower frequency light, which has longer wavelengths, has lower energies. When we use the term spectroscopy, we're really talking about the study of how light interacts with molecules. So in your Chem 105 course, you may have used UV visible spectroscopy, which looks at the absorbance of UV visible light by colored samples. For us in Chem 211, we're going to be using IR spectroscopy to look at energy absorption by particular bonds, and we can then confirm if our samples contain those bonds. So when we think about the interaction of light with our molecules, we can imagine that the molecule is in its low energy ground state. Upon exposure to light, the molecule can enter a higher energy excited state. In order for this transition to happen, it's very important that the exact energy of this light matches the precise energy gap between the ground and excited state. So given that there are these very particular criteria that have to be met, as we look at absorption across a range of wavelengths or energies for particular molecules, it's not surprising that individual molecules with unique structures absorb differently. And we can use those characteristic absorptions as part of our identification and characterization process. So when we're talking about IR light in particular, infrared light nicely matches the energy required to go from a ground vibrational state to an excited vibrational state. So when we're talking about vibrations of a molecule, it's helpful to think of each individual covalent bond. And you can imagine that the two atoms of that bond are like balls connected by a spring. This makes vibration possible. So as infrared light is absorbed by a molecule, the energy from the light can be used to promote different vibrations, such as stretching and bending. So again, at room temperature, we'd expect to be in the lowest state until light exposure promotes the molecule to these excited states. So as we're thinking about how we can use infrared spectrum, we have tables which are linked in your lab manual, which report the characteristic IR absorption values observed for different types of bonds. So we can use these reference ranges to compare to our own data and see if those bonds are present. So with this background knowledge, let's take a look at a real-life infrared spectrum. So this is the spectrum for the alkane octane. So let's point out a couple of features about the spectrum. You'll notice that on the y-axis, we have percent transmission. So if we think about our fundamental principle of spectroscopy, we have an incident or incoming light, which is then exposed to our sample. And we know the light that came in, and we can measure how much of that light has passed through. So at high transmission, we have these flat areas that are higher on the y-axis. That indicates that at that particular energy, there was no absorption by our molecule. So this is little to no absorption. What we're particularly interested in when we're identifying bonds that are present are these dips in the spectrum, such as this shown in pink. This indicates absorption and tells us that we have a bond that's capable of absorbing light at that particular energy. So when you place your sample into the infrared instrument, The instrument is going to allow each unique energy within the IR region of the electromagnetic spectrum to pass through your sample. And we're observing the possible absorbance at each of those unique energies. For this reason, the x-axis is really a measure of that energy, and it's reported in wave numbers or inverse centimeters. So as we go from 500 to 4,000, the energy is getting higher. So now that you know how to read a spectrum, let's start to take a look at how specific functional groups and bonds will present themselves. So starting with this alkane, we find a bunch of sp3CHs. You'll notice that the absorption for these is between 2,800 and 3,000. We can also take a look at a molecule which contains an alkene, which has sp2 carbons connected to each other. And this particular alkene does have sp2CH bonds. So if you come over to 3,000, you still see the absorbance between 2,800 and 3,000 for the sp3CHs. So those sp3 carbon hydrogen bonds are absorbing energy in that region and using it for their stretching. Just above 3,000, that's where we're going to find the sp2CH stretches. And I like to think of drawing an imaginary dotted line right here at 3,000. And I look to the right and left of that line when I'm trying to confirm whether my molecule does or does not have sp2 carbons present. You'll notice so far we haven't talked much about the lower region of the spectrum, particularly from about 1,300 to 500. There are peaks there, so they could be interesting. However, this region often gets messy, and it can be hard to tease out the really important information that's buried within there. We call this the fingerprint region. Much like our own fingerprints, there is a unique signature that corresponds to each individual molecule sort of embedded within here. But again, it can be really difficult with your naked eye to get the important information from that. So we're going to focus on some of the signals that are a little easier to recognize. And speaking of easily recognizable signals, the alcohol gives a really nice diagnostic signal. And when we're thinking about an alcohol, remember that it's a polar OH bond that's capable of hydrogen bonding. For this reason, we see it at the higher energy end of the spectrum, typically between 32 and 3,500. And as you're looking here, this would represent the absorbance that takes place, and the energy from that absorbance is used for OH stretching. Notice the characteristic shape of the OH. It gives a smooth, broad peak. And so it's pretty easy to recognize. You could also see in this spectrum that we've pointed out the CO sigma bond. Again, because it's buried in this lower region, it can be one of the ones that's more difficult to recognize. So when you're identifying an alcohol, your main focus is going to be looking for the OH stretching. And then, of course, because we have sp3CHs, we see the stretching in the appropriate region for those. Another functional group that some of you may be hoping to find in your unknowns is the carbonyl. And remember that carbonyls can include ketones, aldehydes, and esters. So what you'll notice as you look at this IR spectrum is that there's a distinct absorption at about 1,700. So different types of carbonyls will come in the 16 or 1700s, and they typically give strong absorptions, meaning the bottom of the peak is often at a low percent transmittance along the y-axis. So as you're looking at different possible carbonyls, the table in the lab manual will give you a little bit more information that can help you distinguish, say, an aldehyde from a ketone or an ester. If we move to the carboxylic acid, you'll notice that it's actually a little bit more of a complex functional group. And the reason for that is it contains both a carbonyl and an OH. And what's important in the carboxylic acid is that the OH is directly attached to the carbon of the carbonyl. So based on what you've seen in the previous slides, because it does have a carbon-oxygen pi bond and it does have an OH bond, you're probably expecting to see signals similar to the ones we've seen before. So let's look for the CO pi stretch. We do in fact see that right here. And then if we look for the OH and we're expecting to see exactly what we saw for the alcohol we previously looked at, we might be a little surprised. There is something happening in the OH stretching region. Okay, so again, getting above that 31, 3200. However, you'll notice that the shape of this is nowhere near as smooth as what we saw for a typical alcohol. There's a lot of hydrogen bonding that's possible for carboxylic acids. And one of the things you'll notice is they give a broad peak, but it's really messy. So it's a messy and broad, and it almost takes over that sp3 stretching region just below 3000. So when you see this shape, and then you also see a CO pi stretch in the 1700s, those two together are pretty indicative that you do have the carboxylic acid functional group. And the last specific data we're going to look at in this video is for an amine. So those of you who have a basic organic molecule after coming out of your solubility tests are probably going to be looking for some evidence of an amine in your IR spectrum. So for the amine, much like for the alcohol, we often have a very polar NH bond shown here. And this is known as a primary amine because this nitrogen actually has two NH bonds. Again, because it's a polar bond with hydrogen bonding capabilities, it's no surprise that we see it in a similar region of the spectrum where we see the OH stretching. So this higher energy region is often known as the hydrogen bonding region, where we find our OHs and NHs. And if you look closely at the spectrum, you'll actually notice that for primary amines like this one, it's not uncommon to individually see each NH bond give a separate peak. And then of course, as you're getting familiar with already, here are your sp3CHs. And there's not much that we're going to find in the fingerprint region that's going to stand out, obviously, to help tell us quickly that we might be having an amine present. So you can take a look at the IR appendix linked in the lab manual. It'll list different functional groups and the approximate ranges in which you would expect to find an evidence of absorption if that functional group is present in your molecules. And hopefully this will help you get one step closer to identifying the structure of your unknowns, and you'll get some extra practice with this in the coming weeks and as the semester progresses.